Golden Iris Productions presents Gravitational Scaling at the Bohr Radius, Bohr-scale gravitational normalization by Mark F. Dennis. We begin by setting the stage. Today we explore a question that sits at the intersection of atomic physics and gravitation. Can gravity, when viewed at the scale of the Bohr radius, reveal a meaningful scaling structure, or does it simply remain negligible compared to electromagnetism? This presentation, Gravitational Scaling at the Bohr Radius, examines that question through direct numerical and dimensional analysis.
Motivation. For centuries, physics has been defined by a striking imbalance. Gravity is extraordinarily weak compared to electromagnetism. At the same time, quantum mechanics is built entirely on atomic length scales, where electromagnetism dominates. This leads to a natural question. What happens if we evaluate gravitational coupling not at astronomical scales, but at the Bohr radius, the fundamental length scale of atomic physics? To investigate this, we examine the scaled quantity involving Newton's constant g normalized by the square of the Bohr radius. Fundamental constants. We now establish the constants that define our system. The Bohr radius A0 sets the characteristic scale of the hydrogen atom and is approximately 5.29 times 10 to the minus 11 meters. Newton's gravitational constant g governs the universal strength of gravity, but is known to be extremely small in magnitude at microscopic scales. These two constants anchor our comparison between quantum and gravitational regimes. Evaluation of the expression. We now directly evaluate the scaled expression numerically. The Bohr radius enters squared in the denominator, dramatically amplifying the scale of the calculation. When combined with g and the prefactor, the result yields a value on the order of 10 to the 22 in SI units. This is not unexpected. It reflects the extreme sensitivity of dimensional scaling at quantum length scales.
Dimensional analysis. It is important to understand what this number actually represents. The gravitational constant carries units of cubic meters per kilogram per second squared. Dividing by the square of a length reduces this to meters per kilogram per second squared. Thus, the result is not dimensionless, nor is it a conventional physical observable like energy or force. Instead, it represents a scaled gravitational coupling per unit mass and length. Comparison with quantum energy scales. To place this in context, we compare it with known atomic scales. The Rydberg energy defines the characteristic energy scale of hydrogen at approximately 13.6 electron volts. Electromagnetic forces at the Bohr radius dominate atomic structure, governed by Coulomb's law. By contrast, gravitational forces between electrons at the same scale are many orders of magnitude smaller. Even when amplified by large numerical prefactors, gravity remains fundamentally suppressed in atomic systems. Classical acceleration at the Bohr radius. We now consider the classical Coulomb acceleration of an electron. At a distance equal to the Bohr radius, this acceleration reaches approximately 9 times 10 to the 22 meters per second squared. This value serves as a useful benchmark. It reflects the natural dynamical scale of electron motion in hydrogen. Interestingly, this scale coincides numerically with the earlier gravitationally scaled expression, though the underlying physics is entirely different.
Why the number 3.79 times 10 to the 12 matters. We now examine the origin of the large numerical factor appearing in the derivation. This factor acts as a strong amplification term, arising from combinations of fundamental constants. Such numbers typically emerge from unit conversions or intermediate symbolic simplifications. However, it is crucial to emphasize large dimensionless numbers alone do not imply new physics, unless all units and dependencies are physically meaningful. Interpretation. The key insight is that this expression does not define a new constant of nature. Instead, it serves as a bridge quantity, a comparison tool between gravitational and electromagnetic regimes at atomic scales. Its meaning only becomes physically relevant when combined with a mass scale or energy scale, such as the electron mass or Planck-scale quantities. In this sense, it functions as a diagnostic ratio rather than a fundamental law. Conclusions. We find that the scaled gravitational expression evaluates to a large numerical value on atomic length scales. However, this does not indicate a strengthening of gravity. Instead, it reflects how dimensional scaling can amplify small constants when evaluated at extremely short distances. The key conclusion is that gravity remains vastly weaker than electromagnetism in quantum regimes.
Outlook. Moving forward, a more meaningful analysis requires non-dimensionalization using fundamental constants, such as the mass of the electron, me, h-bar, and c. Comparisons with Coulomb coupling strengths may provide deeper insight into scale hierarchies. Such approaches are often used in attempts to explore possible connections between electromagnetic and gravitational frameworks. The question remains open. What structures emerge when all fundamental interactions are expressed in a fully dimensionless form? Transition into derivation section. We now shift from interpretation to derivation. We begin with a composite expression involving fundamental constants, including the fine structure constant, Planck-length, and electromagnetic parameters. Our goal is to systematically eliminate intermediate variables and reveal the underlying structure of the expression.
Eliminating alpha. We start by rewriting the fine structure constant in terms of fundamental electromagnetic quantities. Substituting this definition allows us to remove alpha entirely from the expression. What remains is a formulation purely in terms of charge, mass, permittivity, and Planck-scale parameters. Next, we eliminate the speed of light using its electromagnetic definition. This transforms the expression into a purely field-theoretic form involving permittivity and permeability. At this stage, relativistic structure is fully embedded in electromagnetic constants. We now introduce the Planck-length relation. This step is critical. It bridges quantum mechanics, relativity, and gravitation. After simplification, the expression collapses into a form proportional to Coulomb strength divided by gravitational coupling. The resulting numerical value is approximately 3.79 times 10 to the 12th. We define a useful intermediate quantity, the electron Coulomb constant. This represents the Coulomb interaction strength normalized by electron mass. It provides a direct bridge between electromagnetic force and inertial response.
Coulomb acceleration. We now express acceleration in a compact form. The classical Coulomb acceleration becomes inversely proportional to the square of distance. This reformulation highlights the simplicity of inverse square dynamics when expressed in constant form. At the Bohr radius. Evaluating at the Bohr radius yields the characteristic atomic acceleration scale. This value defines the dynamical environment of the hydrogen ground state. It is one of the central reference points in atomic physics.
Bohr radius. We begin with one of the most fundamental length scales in quantum physics, the Bohr radius. It is defined as approximately 5.29 times 10 to the negative 11 meters. This is the characteristic orbital radius of the electron in the hydrogen ground state. It is not an arbitrary distance. It emerges directly from the balance between electrostatic attraction and quantum angular momentum quantization. In many ways, the Bohr radius defines the natural geometric scale of atomic structure itself. Electron Coulomb constant. Next, we define the electron Coulomb constant. This quantity combines the Coulomb force constant, the elementary charge squared, and the electron mass. Its significance is straightforward. It measures the strength of the electron's electromagnetic interaction per unit mass. This allows us to treat Coulomb attraction as an acceleration field rather than simply a force law. It becomes the natural bridge between electrostatics and electron dynamics. Coulomb acceleration. Using this constant, the classical acceleration of an electron at distance r becomes remarkably simple. The acceleration scales as the inverse square of distance. This is exactly what we expect from any inverse square central force. But here, the expression is written entirely in terms of measurable physical constants. This makes it a direct descriptor of how strongly electromagnetism drives electron motion at any scale.
Acceleration at the Bohr radius. Now, we evaluate this acceleration at the Bohr radius itself. This gives the classical orbital acceleration of the electron in hydrogen's ground state. This is an enormous acceleration, far beyond anything encountered in ordinary macroscopic systems. And yet this value is entirely natural at atomic scales. It reflects the extraordinary strength of electromagnetic confinement in quantum matter. The meaning of A0 squared. Squaring the Bohr radius gives us the fundamental area scale of the hydrogen atom. This quantity appears repeatedly in electromagnetic normalization. It defines the geometric suppression factor that controls how inverse square fields scale at atomic distances. Whenever we divide by A0 squared, we are effectively projecting physical interaction strength onto the natural area scale of quantum structure. This is why it appears so prominently throughout this derivation. The simplified expression. After applying the necessary substitutions and cancellations, the original composite expression reduces to a remarkably compact form. What began as a complicated product of Planck-scale, electromagnetic, and quantum constants collapses into a simple scaling relationship. This is important. It tells us that the apparent complexity was only structural. Beneath it lies a much simpler physical connection between atomic geometry and electromagnetic acceleration.
Setting r equals A0. When we set the radius equal to the Bohr radius, we are evaluating the system at the exact scale of the hydrogen ground state. The resulting magnitude is extraordinarily large. This reflects the intense localization of quantum electromagnetic energy at atomic dimensions. It is not a new physical force. It is simply what classical scaling predicts when applied at quantum length scales. The number is large because the Bohr radius is extremely small. Setting r equals 1 meter. If the radial dependence is removed earlier in the simplification, the expression reduces to the Coulomb acceleration normalized directly by the Bohr radius. Numerically, this gives approximately 9 times 10 to the 22nd meters per second squared. This value is striking because it matches the expected classical electron orbital acceleration. This agreement is not accidental. It confirms that the derivation is internally consistent. The mathematics has returned us to a physically meaningful atomic quantity.
The full expression. We now return to the original expression. At first glance, it appears highly complicated, containing Planck-length, vacuum constants, charge, quantum terms, relativistic terms, and atomic normalization. But after systematic substitution, every apparent complexity cancels cleanly. What remains is not an exotic mu law. It is a hidden reformulation of familiar Coulomb acceleration at atomic scale. That is the central mathematical result. Final conclusion. What have we learned? We began with an expression that appeared to connect gravity, quantum mechanics, and electromagnetism through Planck-scale normalization. After simplification, we discovered that it reduces precisely to the classical Coulomb acceleration structure of the electron at the Bohr radius. This is significant for two reasons. First, it confirms the internal consistency of the derivation. Second, it shows that seemingly exotic combinations of fundamental constants can sometimes encode well-known physical behavior in disguised form. The result does not reveal new physics, but it does reveal something valuable. The constants of nature are deeply interconnected, and when properly normalized, their relationships often collapse into elegant physical truths already hidden within established theory. The Bohr radius is not merely a quantum length scale. It is a natural normalization boundary where atomic geometry, electromagnetism strength, and inertial response converge into a single measurable structure. And that convergence is what this derivation ultimately reveals. Final conclusion. What have we learned? We began with an expression that appeared to connect gravity, quantum mechanics, and electromagnetism through Planck-scale normalization. After simplification, we discovered that it reduces precisely to the classical Coulomb acceleration structure of the electron at the Bohr radius. Second, it shows that seemingly exotic combinations of fundamental constants can sometimes encode well-known physical behavior in disguised form. The result does not reveal new physics, but it does reveal something valuable. The constants of nature are deeply interconnected, and when properly normalized, their relationships often collapse into elegant physical truths already hidden within established theory. The Bohr radius is not merely a quantum length scale. It is a natural normalization boundary where atomic geometry, electromagnetic strength, and inertial response converge into a single measurable structure. And that convergence is what this derivation ultimately reveals.